Hello. In this poster, I'm going to explain, I will investigate what you lose when you gamble. So even in the situation of a fair gamble, we lose something. We lose position in the Lorentz ordering. So here we have a Lorentz curve. The Lorentz curve is used in economics to measure inequality in the wealth distribution of a nation. For example, the Lorentz curve L2 of you says 20% of the poorest people in the nation have 2% of the wealth, whereas 20% of the richest people have 50% of the wealth. So our claim is that Lorentz curve, a gambling, takes you downstream in the Lorentz ordering. For example, if you start with a distribution x1, which corresponds to the Lorentz curve L1 of you, and you want to achieve a target distribution x2 of your wealth, which corresponds to Lorentz curve L2 of you, there is a sequence of fair binary gambles which take you from L1 of you to L2 of you. However, in this particular example, L1 of you greater than L2 of you does not hold. So you cannot go downstream. You're not going downstream, hence there is no sequence of fair gambles that can take you from x1 to x2. So this is our main theorem. Now the second problem that we consider is how we minimize the amount of money we place on the table while going from initial distribution to a target distribution. So we start with $1, and our target distribution here is a uniform distribution. Our wealth has to be uniformly distributed between $0 and $2. We propose two methods to achieve this target distribution, and we show the method 2 is better than method 1. In here, we use only physical gambles. We first bet $half, then a fourth, then an eighth, and so on. And in the end, we have a distribution which is uniform between 0 and 2. And we have placed on the table a total of half plus 1/4 plus 1/8 plus so and so, which sums to $1. And in the second method, we use a YAR gamble. We use a book of random numbers to generate Y, and we bet $Y. Our wealth is 1 plus Y or 1 minus Y. And we see that when we use YAR gambles, we have a total of $half invested, which is less than the $1. Hence, we conclude method 2 is better. So we place lesser money on the table. And so in the end, we want to talk about how you, we will go to unfair gambling, when the casino is offering a host of gambling menus, and we show a gambler can strategically combine all these gambling menus and come up with something better. But that is a situation when the gambler cannot do better, and we show that here, the casino offers, you put in X dollars, you get $1 with a probability f of X. As long as f of X satisfies this necessary and sufficient condition, no strategy can help you do better. So, we give a very simple example where the house has a fixed percentage of house stake, and a strategic gambler can combine these gambles strategically and make it better to get a better probability of winning. He could combine many unfair gambles to get a better probability. And this f of X here satisfies the stability condition, so you cannot do better than this. We have achieved the best. So thank you very much for the opportunity, and I hope you enjoyed the talk.